So last week was all about inputs, and this week is all about outputs. So we're going to try and understand a little bit better the other side of how your Arduino projects behave and how they produce things, how they do stuff. And so we're going to just run through a whole bunch of examples, and I'm going to try and give as many examples of projects as I can to think about what's going on. Another thing that's kind of fun to do while we're having this discussion is to, let's see, pop into here. And if we go to Instructables, Arduino, and I'm searching this on the wrong window. I know that's true. Here we go. If we go into this, one of the things that I think is it's a weird and nerdy game, but it's a fun game, is to run through projects and like try and identify what their inputs and outputs are, right? Like in this case, open source telepresence bot, this looks like it's an iPhone on wheels. So motors are definitely the output. This is a drawbot, and this is a drawbot wrapped around an egg, which is a fun project for sure. But here's a servo motor, that's its output, and then there's some motors to spin the egg and to move this thing back and forth. So 3 motors, and you've got the ability to draw on eggs. Here's a little, let's see, what does this say? Watering system with remote control and clock. It's got an LCD and a motor, and that's probably it. Just running through and looking at making a clock with a hard disk drive. That's pretty fun. This is probably just like this little screen down here. And then you can buy motors for clocks to put in there that are steppers that I think it can control. Here's Arduino school bell. Oh my goodness, that sounds wonderful and terrible all at once. This is a relay. So this is like a full power switch, and then some other stuff in here that's a little terrifying to have all in the same box. But just like running through projects, looking at what they're telescoping, conduit pull extension, sensing photoresistor. It's just fun to go through and sort of imagine what their outputs are and what their inputs are on projects like this. And then you can open them up because it's instructables and really read to see what it says. Like the friendship lamp, this is one that's worth clicking into. The output is definitely just that LED. And I think for this particular one, you can send a message over I think the way that this one works, if I remember reading this one a while ago, is that you can connect devices and like send a message to a friend and their lamp will change colors. So like you have a friend network of lamps, which is really cool. And basically it's just going to be boiled down to like, here's your message sender, there's your lamp, and then, or this is probably your message selector, a knob and a button. So some sort of a fun thing where you can get messages sent back and forth, just simple like thinking of you, change your lamp color sort of features. You know, there's a ton of cool projects out there, and just sort of wandering through what their inputs and outputs is a lot of fun. So we're going to have mostly a very similar format to last week. We're going to go through 25 outputs, try and see what they all are, talk a little bit about some of the core concepts, then run through 6 essentials that if you really wanted to master 6 things, they'd get you a long way. Then we'll talk about motor controllers, because motors, it turns out, are tricky. A little bit about libraries and protocols, and then some tricks. So we're going to just try and buzz through and say as many words as we can. If you've gotten any questions, you've run into projects that you're interested in doing, and you have questions that you want to ask, feel free to stop me at any point and ask. So here's the panel of 25. So I'd like to break these into motors. There's many classes of motors, but the motor class, and then a light class. So for LEDs, bulbs, and those sorts of things. There's some weird non-standard motion stuff. Arduino is often centered around things being weird and fidgety. And in my mind, part of that is getting things to move. So there's other ways that you can make motion happen. Then there's power. So there's all sorts of powery things that you can do that really control the flow of electricity in a much bigger sense than an Arduino. And then audio video. So all of this cool stuff that's over here. So just running through, we're going to talk more about the blue ones. So I'm going to, and these yellow ones. So I'm going to whiz through and quickly talk about all the other ones. Like a DC brush motor is the normal motor. We're going to get into that in a minute. But then a brushless motor, this is like a drone motor. So it's a slightly different type of motor to use with a drone. Brushless ones, brush motors have things that physically contact each other, that brush up against each other. it makes them cheaper to make, easier to run. They were the first type of motors that were invented. And so brushed motors are really a good way to go with lots of projects, but brushless motors are a little bit more complicated to run, but they can run higher speeds, higher torque. They're less likely to break down over time. They're altogether really clever. The PC fans that everybody's got, those are brushless PC fans almost exclusively. So if you've got a fan in your computer that makes noise, it's a brushless one. Let's see, then there's servo motors. We're going to take a look at those. Stepper motors are close cousins to the brushless DC motor. They're brushless also, but in a slightly different way. Industrial servos are a really cool thing. Those are what power the Gerber. It's essentially sort of a blend between a big stepper motor and a servo. If those two had a baby that was very large, it would be an industrial servo. It's a motor where you know where it is and you can get it to move to different locations. Then light and LEDs. We've definitely talked about LEDs before, so we're not going to go into the weeds real far with these, but they're a cool way to have outputs in your Arduino projects. You can have single LEDs where they're just one thing on its own, like pin 13 on the Arduino board, RGB LEDs, addressable LEDs, incandescent bulbs, like a regular old light bulb. And then there's a ton of other weird bulb technologies that you can use, the funkier lights that you can try and control. Then there's non-standard motion is a fun category. Pneumatic actuators, we use that on different things around here. If you ever hear a psh, like a puff of air, like a psh sound, that's a pneumatic actuator happening. They're all over the place in different machines and different places. The Gerber uses it to hold its tool and to do different actions. The Country Bear Jamboree uses them. If you listen closely, it's a little terrifying because you can hear the pneumatic actuators for that. And Chuck E. Cheese, it's just, it's best if the sound stays loud in those rooms so that you don't hear the mechanics of it. Hydraulics are another fun one that you can get hydraulic systems to work. For Arduino, these are often really tiny ones, but they could definitely be in charge of full-scale hydraulics, like to lift things. Solenoids are a fun category. These are sort of the simplest motors. They just move a magnetic slug in one direction to punch something. And where they're commonly used is as doorbells. So you can have any sort of shape bell, a very traditional physical bell, and then a solenoid will sort of slam a little metal piece into it to make it ring. They're absolutely how doorbells have worked for a long time. There's an aisle section for them at Home Depot or Lowe's if you wanted to walk in and buy one. Nylon muscles are really cool, and I'm going to pull up this link, but nylon muscles are these interesting things where you can take nylon or some different things and you can heat them up and cool them down. And when you do that, if you heat them and cool them, they'll expand and contract. So there's a bunch of different things that you can do. And I think this is maybe one where they're spinning it. And so they're using fishing line to make sort of a muscle that will contract. There's also these like memory wire. There's these other weird nitinol memory wire. This stuff is another crazy, let's look up nitinol so that I get the name right. Well, it's for jewelry, but it's also something that you can get to do electronics with. If you conduct and Lisa, you're probably very good at dealing with nitinol, managing its temperatures just right. But you can take nitinol wire, set it at a certain temperature, and then it will remember that shape. And then you can deform it and put it back to that shape with a little bit of current. And so I've seen some really beautiful, elegant, and I would have to dig to find it. I should dig and find it, but some really elegant displays where those are used to make butterfly wings flap in a piece of art. So like you just conduct a little bit of heat through them and they can change their shape. They sort of act like springs that'll let the butterfly wings go up and down. And so you can silently and very elegantly make some cool things happen. It's fun. So memory wire, nylon muscles, those sorts of things have some really cool non-standard ways to move stuff around. It's a lot of fun. We're going to talk about relays. Basically, if you want an Arduino to flip a light switch for you and you don't need a physical light switch to be there, the relay is the classic way to make this work. Relays have been used for a long time in lots of different formats. If you open up an old school pinball machine, there are relays everywhere inside. I used to have a good friend who was very into recuperating pinball machines, and so they were constantly buying different size relays. Those are a very analog process, though. It's basically a solenoid and a switch put together. A solid state relay is sort of the new version of that, where it's a big beefy transistor that switches power on and off. Then there's heaters. You can definitely apply power to heat something if you wanted to do that with an Arduino. You just need to be careful about how much power is flowing. And then transistors and motor controllers are how we actually do a lot of that power switching. We'll get into those. Audio video, there's tons of cool things in this space. Speakers, every one of the Arduino kits that we gave you has a little speaker in it. And if you haven't yet found that you can find the code to make the Mario song come out of your Arduino, you should totally do that because it's lots of fun. You plug in the speaker, you upload the code, and it'll just play the Mario theme song for forever. Which is definitely not annoying, certainly not a problem. Then there's the piezo buzzers. These are smaller, simpler buzzers. Not really speakers, just sort of a buzzer thing. And I think actually this is the part that comes in your, if these are both here, a speaker is like the speaker you're used to seeing from a car stereo, and a piezo is the little thing that came in your Arduino kit. Video, the Arduino can actually output video, very low resolution and not with much going on, but it can draw graphics for you. But think about like a circle moving across the screen or like a triangle changing shape or color. It's definitely not, you're not going to play a video game of any real substance on an Arduino. But one cool feature is that they're really good at putting text on screen. And so if you have something that doesn't need to be updated that well, OLED screens are really low energy. They work super well. They come in all shapes and sizes, and they're lots of fun. Another one that's really cool is e-ink. So I don't know how many of you might have a Kindle sort of thing, but if we look up e-ink display, you can buy the screen from a Kindle, basically. And so I'm just going to go to images and we'll look at this. But here are e-ink displays. You can buy these. Sometimes they're flexible, sometimes they're on a circuit board. But this like Paper Pro, sometimes they're multicolored. These are displays that you can buy from Adafruit or other suppliers and be able to display things. These have a very slow refresh rate. However, one cool thing about them is the way that they work. They're like, imagine a little cell with ink globules that can either float to the top or float to the bottom. And if you want to draw something, they float to the top. If you want to undraw something, they float to the bottom. But it doesn't take any power to keep them where they are. So you can draw a picture and leave the whole thing completely unpowered, and it will hold that image. That's why a Kindle can leave a picture on the display and it just sits there without sipping any battery. That's why their battery life is so long. A Kindle really only needs to apply power to its display when it's changing what's on the display. So it's a really cool effect to have. And e-ink displays like this, I mean, this is, I would just give a price. Here's the Amazon link for this one, $20, which feels like you're paying too much. But you know, you can get cool displays like this that give you all sorts of functionality to add in. If you wanted to have something that can just display like the weather or whatever, you can have a really cool, here's a tricolor one, there's different versions. This looks like it's probably all buttoned up, just the fact that it's got a USB and that's it. But what a cool, it's a cool way to add some information to a project if you want to have an output. So those are the 25 like big idea projects or different things. If you want a more complete list, this is linked here. I'm gonna, if I have, I don't know if I put this link into the chat, but I will put the link to these slides in the chat right after so that you can check that out. But it's definitely a much longer list. Let's say you want to output something in one way or another. The first thing that you're going to need to know about, aside from just some of the basics for code, is how do you make these things work? What's going on? And one of the first things you're going to come up with is pulse width modulation. So pulse width modulation is the way that we can get an LED to fade. And so it's when you fade an LED, you make it go between bright and dim. And so bright and dim is something that you really can't do well with an Arduino. But the benefit is that Arduino can pull it off. They can trick you because it can blink faster than your eye can see. Your eye sees at about 30 frames a second and no faster. Like you can buy a TV that's 60 frames per second or 120 or 240, but really it's diminishing returns. Your eye sees at like 30, 35 frames per second. Beyond that, it just can't see it. Versus the Arduino that can blink on and off like thousands of times per second. And so the Arduino just takes control of the fact that your eye is going to average out what it sees and give you a general impression of what's going on, so it can simulate analog voltages. Voltages that you could shift around, like between 12 and 2 volts, they would let you control the speed of things. So like, here's your fan motor from a computer, or here's other motors in your life. If you wanted to change the speed, like on a drill, you could apply different voltages out of the battery. So you could turn it on all the way and apply 12 volts, or you could turn down the amount of power that it gets. And then you'd come down to 2 volts, a very low voltage, and it would be slow. This used to be for the ceiling fans with knobs in the wall, and this is not standard anymore. They used to control the speed of a ceiling fan with a knob that was a continuously turning potentiometer in the wall that would limit the voltage applied to the motor of the fan. That is a well-intended thing that would give you exactly this effect, where you could, if you cranked it all the way up, it would get full voltage, all 110 out of the wall, and it would go real fast. If you cranked it real low, it would turn off, and at some point in between, it would run real slow. But the thing about that is that then all of the power is being consumed, and usually the reason why those aren't standard anymore is because the switch would get hot because it was dissipating a lot of energy. Now we do this by simulating voltages instead of being able to actually hit those. We just spend different amounts of time with the power on and off. So the Arduino simulates this output of 5 to 0 volts by shifting around how much time is spent on or off. And so if it spends all of its time on, it looks like it's full power. And if it spends half of its time on, so it's going through cycles a bunch of times per second, about 1,000 times per second, and 50% of the time it's on, 50% of the time it's off, it's going to look like it's 2.5 volts. Let's look at how this looks. So Arduino can't do full modulation of its power, but what it can do is this pulse width modulation. So there's systems inside the Arduino that blink at a cycle of 490 hertz or 980 hertz. These are built-in features to the Arduino that let it do the fading LED. And so if you're wondering how all this works or where this comes together, you can do Arduino examples fade. And so if we come into here and do fade Arduino, here's the fade example. It demonstrates the use of analog write for fading an LED off and on. It uses pulse width modulation, turning the digital pin on and off very quickly to create a fading effect. So it's typically plugged into pin 9 as the default for this. And inside of the code, Arduino does some of the heavy lifting for you. It just says that we want to analog write some brightness amount. And this is some number that has to be between 0 and 255. And as long as you give it some number between 0 and 255, 0 is all the way off, 255 is all the way on. And your like percentage of the way up to 255 is your percentage of the power applied. So in here, if I analog write 0, basically that means that the pin is off all the time, and the LED would look like it's off. If it's 25% duty cycle, I would be analog writing 64. And that means that only 25% of the time in each cycle is it turned on. And then the rest of it, the other 75% of the time, it's turned off. And so it turns on for a little bit, and then it turns off, and it stays off until it realizes, oh, the next cycle started, then it turns back on. Waits for 25% of the time, then it turns off again. And you get this net effect that on average, all the points in this line are about 25% of the way up to the 5 volts. At the 50% duty cycle, each time it hits a new cycle, it's on until it hits halfway through, then it goes to off. And if you were to average all the points up here and all the points down here, this would look like it's running at 2.5 volts, halfway between 0 and 5, so that it's simulating sort of giving a partial voltage. 75%, it's on 75% of the time, and 100%, you're analog writing 255, the top of that range, and that just looks like it's turned on. And so inside of here, we can totally just steal this code and plop it into, let's grab this and go right into Tinkercad and make it work. So we can play around with this, and Tinkercad's going to take a second to load. Oh, while we're doing that, we can create a new circuit. I think I have one in here, maybe. Well, we're doing it now. So in here, we can grab one of these Arduinos and play around and just get a couple of features. It doesn't take a lot to get this to work. We just need an LED and a resistor, and we'll plug our resistor right into ground, and then boop, click, and this into pin 9, and then go into our code, and hopefully I didn't wire that in backwards. Yes. And we'll just paste that in and start the simulation. Oh, I missed my variable. So we'll do int LED equals 9. So just running this, it's going to be able to, and brightness and fade amount. Oh, I missed the variables. Up here. There we go. We'll just grab them. So these we can take and throw right into the top of this sketch. And so now I've got those that'll run. And you can see it's on, and then it sort of fades to off and then fades back. One of the features of this is that it's not super clear exactly what's happening. And so what I can do is come in and say, let's do serial begin 9600. And so with this, we can go in and just spit out what's happening. So serial, this, if you haven't started playing around with the serial monitor too much yet, the real benefit is that you can put in information so that you get out what you want. So in this case, it's going to print back to me the brightness. And so if I start the simulation and then run the serial monitor, you can see it's sort of going up and then down through these numbers. And as it does that, the brightness up here matches with the scale of the number there. So it's able to sort of simulate applying a high voltage or a low voltage based on the numbers. That's a little fast, so I want to slow it down just a bit. So delay 30, let's do delay 100, and then start this again. But you'll see that it's starting and then it's sort of climbing its way up. It's not very bright, and then it hits 255 and it's as bright as it's going to be. And then it sort of dims back down as it gets back down to 0. This is way more pronounced with a real one, by the way. If it's physically in front of you, it's a lot easier to see. But this is a great way to sort of wrap your head around what's going on without needing to have a thing in front. So pulse width modulation lets you play around with LEDs and turn their brightness up and down, but it works exactly the same for a motor. So you can have a motor run at high speed or run at low speed or somewhere in between, as long as you do this analog write feature that lets you control its speed. Now it's a thing that's physically built into the pin, so not every pin has it. Only these ones marked with a tilde can do pulse width modulation natively. You can totally build it in with software if you wanted to do it yourself with delay microseconds and some of those things. You can do it, but these are the ones where you get it kind of for free. And analog write just works. It's 11, 10, 9, 6, 5, and 3. And there's only 6 on this type of Arduino, but you get a different Arduino, and some of them have it on all of their pins. So it can be really nice in some cases. So now we understand a little bit more about pulse width modulation, and these are just going to be a start to the 6 core things. But a brushed motor is a prime example of where you'd want to do this. So if you now you're empowered with the ability to turn the power up and down, a brush motor is a good place to get started with that. These are the actual brushes down here that touch onto the rotor, which is the spinny part of the motor, and then there's the stator, the part that stays still. It may feel like a lie because of all the things that happen inside of a motor and how much torque they can deliver. Like if you've ever ridden in a Tesla, and I've only done that once ever, but it's amazing how much torque you can get out of an electric motor. All it is magnets, right? And so just like the Insane Clown Posse said, nobody gets it. It's just magic, which is not quite true. We understand it pretty well, but the key here is that you've got the permanent magnets that push up against the electromagnets, and that moves the whole rotor forward. And so that's the core message. We could definitely nerd out on the science for this for a long time, but we're just going to chalk it up to a little bit of science magic happens in there to make this go. It's certainly one of the most important inventions humans have ever come up with, is the brushed motor. Michael Faraday. There's a really good Cosmos Spacetime Odyssey if you want to watch him invent that. It's a whole episode just on this guy. But the motors are just magnets, and that's all that they really are. They're electromagnets and permanent magnets, but essentially it's just magnets happening. The brushes in here make them easy to use. So with your Arduino, if you just plug it into the 5 volts and ground, it's going to go. And it basically, you can control it as easily as an LED. If you want to be a little clunky, a little inelegant about it, plug it into 9 volts to pin 9 and ground, and this will work just like the fade LED example. No difference whatsoever. We could pop over to Tinkercad, but I don't want to do that right now. If that kind of a motor is, it's good, but it just spins for forever. That's great for wheels, especially because you can go and you can stop. But there's a lot of times where you want to move, but you don't want to move for forever. You just want to move a little bit, or you want to change the motion of something, or you want to pick up a leg or an arm. And if that's the case, a servo is the way to go. Servos come in all shapes and sizes, but thanks to the remote control hobbyist world, there is a huge wealth of servos, and they all run on the exact same communication standards. So for this, there's 3 wires for any servo, just like you can see here, orange, red, and brown. And those are your signal wires, or those are your 3 wires. They also come sometimes in black, red, and white. Red is always power, and servos are almost universally set to run at 6 volts because that works really well with 4 AA batteries. And so the red is the 6 volts in, or 5 volts from an Arduino works just fine. The brown or the black is ground, and so that goes into the ground pin on your Arduino. And then the data line is either orange or white in these 2 as shown. And that's the pin that really controls it. So a cool thing about a servo is that if you have the servo library up and loaded, if you've got that running inside of Tinkercad or on your Arduino, you can send it information like, I would like you to move 180 degrees to the right, or I want you to go to position 32. And it will go there and it will try its best to stay in that position until it gets another command, which is really important if you're building a simple early RC airplane, because when you send the controller command, you want it to go and like turn the flaps and stay there. So RC hobby servo motors are built to take a command, move to a position, and then do their very best to stay in that position. There's a lot happening inside them. Like this has got a clear case, so you can see inside. Sometimes they're opaque. I really like the clear ones. There's a motor. This is a DC brush motor. There's no difference there. And it's attached to a circuit board. This little tiny circuit board has on it a potentiometer. There's a potentiometer, which we talked about inputs last week, tied directly to the shaft. And as this shaft turns, it's turning that potentiometer. So this little tiny board inside, which you can think of as its own little Arduino, it has the input from that potentiometer and the output from the motor. And so if the potentiometer says I'm too far to the left, it responds by saying turn the motor to the right. And if it's too far to the right, turn back to the left. There's some really nice things with a servo motor. All you need to do is tell it to go there, and it tries its very best to make it. They're super helpful. They're relatively cheap. If you haven't played with one, absolutely, we have some to play around with here, so we can do it. If you want to make a hand that waves at you, this is probably the way to do it. These are super easy and nice to play with. So servos are great fun. You can also tear them apart, modify them, do lots of things. I had some students one year that built a robot arm completely out of servos, so you can just mount them cascadingly on top of each other, and then you'll be able to build your own robotic arm, which is really cool. And then they wanted to make it a puppet arm so that they didn't have to like figure out all the complexities of the math of controlling that, because that's inverse kinematics is not a joke for controlling robot arms. But what they did is they built a second one out of more servos. They pulled out all the motors and just attached to the potentiometer so they could build an identical arm, but they were just using it as an input, not as an output. So it's an interesting dynamic to play with these, but there's lots of fun to be had with servos. Steppers then are our next type of motion. This is the bread and butter of printers, of office jet printers, 3D printers, your copy machines. Stepper motors are everywhere, all over the place, constantly around us all the time. Any sort of precise motion at all happens with a stepper motor. Servos are cool because they can play around and move and like do RC car things, but steppers are for when you get serious. It takes a little bit more control. You can see there's 3 wires. These are all power wires. None of them are a signal. These are harder to drive. There's more complexity here, but they've got more holding power. They can move a little bit faster than the servos, and they can continuously rotate and keep track of a lot. Stepper motors are definitely, they've got some complexity, but it's worth learning that complexity because then you can make things move around and do whatever you want. They are at the heart of 3D printers and regular printers because they can move, they can move the printing nozzle from one place to the next and have it go exactly where they want it to. So these are really the heart of what makes all of the machines at MakeHaven that are digital fabrication work. Whether it's the water jet, the laser, the vinyl cutter, the Gerber, the Shipoko, all of those are run on stepper motors. And so you get cooler things when you learn how to control these, but it takes some work, a little bit of effort, but it's really rewarding when you can say, move 18 steps forward and you watch a little flag move exactly the right amount. So there's some cool stuff that you can do with these, but it's another level up on the motor game. Then solenoids. And so solenoids are basically just this action. It's a coil of wire that makes an electromagnet. So if you pass electricity through a coil of wire, you get an electromagnet, one that just exists temporarily and not for forever. These are the things that work to make doorbells ring, because if you have a magnet mounted inside with a spring on it, when you activate it, it'll pull the magnet and overwhelm the spring, and it can drive this little green plunger out and hit your doorbell. And then when it's powered off, the spring pushes it back to its starting position. And so you get a self-resetting system that can knock into things. If you take the spring out and let it float through, now you've got a little rail gun. And so, when a high schooler finds that out, they're all of a sudden very excited. But this is the core technology for how your doorbell works. And there's all sorts of cool examples. Let's see if we can find this. Let's go to this on YouTube. Oh, I don't need an ad. While that's going through the ads, let's check in on this code. Oh, here's, skip that. Here's this code that we were looking at before class. This was some code to take all of my GoPro footage and to run through. It ran through all of these folders and it turned them into video files. So it won't open in here, but it ran through all of these photos that are inside of these folders. And so once you get better at code, you can start to take images. You can do all sorts of crazy stuff. But these are images of making the Wacom stand. Yeah, I just lost it for a second. That are turned into videos by just a few lines of Python code. So as you get better and better with the code, you can use it in different ways. Skip this ad. He's still going. Okay. Let's turn this up. You can see these little servo or those little solenoids in there. They're just knocking into these bells, and it's not making any noise here in the room, and it's probably not through there. But I'll absolutely send you the link to this so that you can get it to play. I'm not sure why it's not. Something in my sound settings. Oh, okay. Now it's making noise in the room. But you can see those are home wound solenoids. There's nothing magical about them, but you can totally make your own, which is lots of fun. So we'll just let it be. But in this case, it looks like gravity is probably what's pulling it back. And so gravity is what's going to pull those down. And I can see some magnets here. So it looks like these are magnets on the end of a screw. And then the screw head is what's hitting the copper tube and making the instrument play. But that's a lot. I mean, you could build your own doorbell and have it. I mean, this is a little clunky. It doesn't look the greatest, but it's definitely a cool effect that you could play around with. Let's get back to the slideshow. If you wanted to buy these from a home center, they come in all sorts of sizes. So you can definitely buy them pre-made. You don't have to wrap your own, but it works really well. This is the circuit that I would use. We're getting closer and closer to like the core of how electronics work. And if you're going to do a solenoid or really any coil of wire, you often want to have a flyback diode. So this is the circuit that you'd want to play with. It's not that hard to build. You need a flyback diode, a transistor, and a resistor, and then just to hook them up in the right way. And if you feel like you want to do this, we can totally do it. Also, if you just want like press button solenoid fires, you don't need any of those things. You can just make it so that it's a simple switch that's applying power or not. So It's a cool way to add a little tiny bit of motion to a project. Not a lot, but just enough to make some things happen. Oh. All right. So next up, one of the things that's worth saying about a solenoid is that you can draw a lot of current really fast. And so that's the core thing that you need to be thoughtful about is don't be aware, like just know if you're drawing 6 amps, that's a lot. If you're drawing one amp or 1,000 milliamps, that's still kind of a lot of power. And the way that you'd measure that is with a multimeter. Most of the things that you're gonna, if you follow instructions, you're not gonna be carrying that much current, but it's good just to try and look around to see how much current is this gonna draw. If you can look it up. I'm going to be very surprised if any of you bump up against this. So don't feel like it's an imminent threat. But it's if you look at this and say, oh, now I want to make all of my own smart home products, I would just caution you to pump the brakes there. Do simple little things first, and then you can get to the bigger stuff. But if you wanted to get to the bigger stuff, here's how you do it. You do it with a relay. And so these are relays. This is a mechanical relay. You can see it looks very solenoid-ish. Here's the solenoid inside. It's got a little coil. That coil will magnetically attract the top of this lever that then pushes a switch closed. So your little teeny tiny battery from an Arduino can act on a big thing like wall power and a light bulb through a relay. That way your Arduino electronics never actually are wired up to your main house electronics. A relay can keep those isolated from each other. So if you wanted to try and do this, you could do it pretty safely with an Arduino, provided all your wiring works out just right. Relays come in all shapes and sizes. They were the centerpiece of how we computed things for a long time. And so there's tons and tons and tons of relay versions that you can buy. The simplest ones are these right here, and they just totally work with an Arduino. Here's the Arduino header pins. You don't have to worry about any of the wiring or whatever. This side goes to Arduino. This side goes to your lamp. That's it. And then you can have, last year, Ruby made a lamp that would turn on if the room got dark enough. And so it would trip, when the room got dark enough, it would turn on the lamp, and then it would just hold it on for 6 hours, and then it would turn off again, and then look at the room again to see if it was too dark. So it's a simple input and output. It's sort of a dumb smart lamp, right? It was smart enough to sense its environment. It was not connected to the internet, but it was definitely a cool way to try and get some action into the works. It was also neat because you could see all of her electronics inside the pink bulb of the lamp. It had like a pink glass bulb on the bottom, like a not a bulb, but like the big glass lamps that everyone remembers someone in their life having. She stuffed all the electronics inside of one of those, so you could see it all, which was fun. Be a little careful if you're going to do this with AC voltages, but also if you're totally fine wiring a house or your own lamps, this is a great trick. This is totally worth doing. Number 6, displays. If there's one thing I really think is magical that an Arduino can pull off, it's a display. And so if you have any sort of an output that you want to make on a screen, this is lots of fun. It would be absolutely a nightmare to do if you had to write all of the code yourself, but there's libraries for every type of screen, so you do not need to figure it out. You can just download instructions for how to work with your very tiny OLED or e-ink or LCD screen, and you can follow the instructions and add in the code that you want to make it output what you're looking for. Like this looks like it's some sort of Wi-Fi or Bluetooth signal, or maybe that's sound levels, I'm not sure. But these displays are lots of fun. If you get your hands on one, they're definitely fun to add into projects. You can dial in the brightness on some of them. These usually there's a lot of wires for an LCD, but it's worth the labor because you can just show yourself things from the project, and that's really nice. And then e-ink is just lots of fun. So there's all sorts of different display technologies. They're really cool. There's even Adafruit has added more and more of these, but let's see, Adafruit LED display. You can buy the displays, these LED matrix displays, these sorts of things. This is the kind of deal that's sort of in the mid-range of, it's a screen that's big and fairly far away, not like the Jumbotron that you'd have at a baseball park, but this is for if you want to display something from 10 feet in the air, these sorts of matrix displays can really do a nice job of that. It would be fun to put one of these in MakeHaven that greeted the person who swiped in to the room, or like that you could turn on, and when somebody walks in off of Chapel Street, there's a series of these that like glow and point them in the right direction. Could be lots of fun. Our stickers work without any power, but this is a cool way to make it work. They sell these at all sorts of scale and size, so you can get all sorts of different displays. There's tons and tons of options. You can get displays for all sorts of things. This is for a Raspberry Pi, but like here's a tiny Arduino one. So you can display all sorts of things. The Arduino is going to have a hard time. This is a very high quality chip that's running this video, but the Arduino can definitely load an image. So if you have a static image, it can load in the colors to pixels. If you just want to display like a photo display, you can do that. Or if you want to do some fun like filtering colors, you could definitely play around in lots of different ways to get different displays to work out the way you want. There's a ton of cool options in this space. But a big thing that you might want to do, we talked about lots of different technologies, but you might want to control a motor. And so if you want to control a motor, there's some theory for how this works. And it's worth it for us just to identify some of these details. The servo is the simplest. You don't need any controllers. They just run. And so those are no problem. If you want a DC brush motor and you only want it to go forward or stop, it's actually pretty easy to do also. But if you want it to be able to drive forward and backward, and almost all the time I want to be able to drive a motor forward and backward, you're going to need something called an H bridge. And an H bridge is just a motor drive. It's what's inside of a motor driver. But you can see this sort of red circuit here. It kind of, if you squint at it in just the wrong way, it looks like an H, sort of. There's a middle bar, and then there's the two sides on the right and the left. It kind of looks like an H a little bit. And here's a little bit more circuit detail. But basically what this particular type of circuit does is it has a strategy that you can use. So that if you have the magenta path, you close switches 2 and 3. So this one and this one are closed. Your power source is going to come through and it moves right to left through the motor. And so we can arbitrarily say that's forward. And then if you instead open 2 and 3, so the motor in the middle isn't connected, and then you close 1 and 4, then you follow the cyan line and you head left to right. So the electricity flows in the other direction, and you're able to control forward and backward with an H bridge. And so there's a bunch of ways that you can do this. You can do it with just one mechanical switch. If you want to physically switch something back and forward, you can do it with a DP/DT switch. But generally, motor controller chips exist for this that let you drive backward and forward. So you could physically build it yourself if you're really into it. But most of the time you just buy some sort of a motor driver and you get this H bridge effect working, because this is essentially the cheat to make it so that you can work your motors forward and backward when really a brush motor is just going to be on or off. But by running electricity through it in the other direction, backwards, by wiring it backwards, it changes its direction. And so without having to physically rewire, this just lets you close different switches, and now you can change the direction of the motor. And so when you're thinking about the drill driving forward, when you press one button and driving backwards with the other button, it is very much an H bridge that's in control of that. So the little chuck that will lock it or drive forward or drive back, that is controlling an H bridge on your drill. So it lets you drive forward or backwards, which is really helpful. However, there's a lot going into that, and physically building one of those is a common problem and a little tedious. So instead, you can buy motor controllers. There's a whole range of motor controller chips, but motor controller chips like this setup will let you drive motors of different types. So like here's a Arduino Shield that you can buy with 3 motor driver chips and then motor plugs right here. And if you wanted to drive 3 motors, this is a out of the box solution that just works. This is one that's specifically for stepper motors. This is commonly used for 3D printers, the DRV 8824 or 25. These are really common to drive. The Prusa, I think, is upgraded from these chips, but in the first generations of 3D printers, this was the standard for how to drive them. You can also do the motor controller, the L298 IC integrated circuit. These little boards are pretty cheap to get on the internet. I think these ought to run you about $3 a board. And this will let you drive a motor. You just apply power to the motor anywhere from 35 volts down to 6, and it will regulate it to 5. So you can run this back to your Arduino for power. Then here's where your Arduino actually sends signal. It looks like this is in Spanish. And then your motor outputs, motor A and motor B, 2 DC brush motors or 1 stepper motor is what you're going to do with this particular driver. You can also build your own, totally. And so here's the circuit to do that if you wanted to do it. It looks very much like the solenoid. This, however, will only go forward. What I have found over my life using motor controllers, and I've done the range all the way from building the little one in the bottom left to once I bought the newest ones. I bought the newest ones I could get from my robot bartender, and I had to sign paperwork saying what I was using them for to the company and government. That was fun. But the you can hit the range of those, and when you're doing it, the more control you have on a motor, the better. And so if you're going to drive a motor and you have access to a motor controller, I would totally recommend you use it. It makes it simpler for you. And usually, like, if you're going to use this one, which is cheap to buy to drive a motor, you can get a Arduino library that will help it happen much easier. So those sorts of benefits from using a motor controller can be really good. Building simple ones like this, though, can be lots of fun and very cheap to use also. So it spreads the range, but I would advise a motor controller if you want to drive one. So libraries. If you want to drive one, if you want to run with one of those DRV 8824s, then you got to figure out how to communicate with that chip. And so the good news is you don't have to figure out all the details. Instead, you let a library solve the problem for you. And this is definitely more true for outputs than it is for inputs. But an Arduino library is code that someone else wrote. And so Arduino libraries can be found in the library manager. And so we can totally pull up the Arduino app and take a look at it there, or we can open up Arduino.io. And so here's the Arduino.app. And so in here, here's the 2 methods. These are my 2 favorite ways to program Arduinos. Here's the Arduino IDE. In from here, you would just go to Tools and Manage Libraries. And when you click on Manage Libraries, you get a window that pops up. And in here, you can search for whatever library you want. And so I'm going to search for encoder. And it will filter through and find all of the encoder libraries that it can find. Some of them are going to be great. Some of them are going to be bad. Some of them are, if you click on more info, they'll take you to a website so you can read all of the details about it. So here's, I just happened to open this one. And not all of them are going to be equally well documented. I would try your best to try and find one that's well documented, or if you find tutorials, they'll often recommend good ones. And if you can ever find one by Paul Stoffergen, definitely get that one. This guy is a powerhouse of Arduino. He's written lots and lots of the major libraries that are out there. Also, the ones from Adafruit are really good. They have lots of good documentation. And so you can get them from there. And that works inside of here. So if you wanted to install those, and if you're using the Arduino IDE, the other thing is that then you get for free all of the examples that come with it. So like, here's the Adafruit NeoPixel, which is a library from Adafruit on how to use those. And here's just a bunch of example sketches that they send, right? So strand test, this is with no adjustment. If I plug in a NeoPixel strip to pin 6 and have at least 60-ish LEDs on it, this will just run. I don't have to figure it. I don't have to do anything. As long as I plugged in the physical things in the right way, and usually there's a preamble that tells you how to do that, this comes in for free if you're using the Arduino IDE. So that's really, really nice. If instead you're running from a Chromebook, and this is commonly a problem for my students, then you might be running from the Arduino app. In here, you can get to libraries just as easily. And so I can search for encoder. I'm just in libraries up across the top. This one from Paul Stoffergen is they're looking at the same list, but the mechanics are slightly different. The downside is that, as far as I can tell, you don't get the example code for free. You'd need to go look at encoder Paul. I'm gonna spell his name real wrong right now. Yep. Somewhere in here, you search around. it's more on you to find the documentation and examples. So the Arduino IDE definitely gets the win there, that by having the particular library installed, you get examples for free in the example section. They do get added at the bottom. So once you have a whole bunch, they definitely start to get bigger. Here's the basic encoder example that comes from Paul. And so here's his documentation. So there's a lot more about it on here. You can go to this website, basic usage, explanation of how they work, some example sketches, all this stuff. It's going to be various documentation from around the web. So definitely be conscious of your libraries and how where they're coming from. However, they're really helpful. Like the Servo library is included by default. You do get some for free. Serial communication and Servo are in there for free from Arduino. And basically, you can just use it without any extra play. So here's include Servo, and then you declare your Servo object, and then there's some methods. If any of you know how to program in JavaScript or Python, this should feel like a natural format. It is lesson number 10 in the sequence if you made it all through that far. But this is, you're just instantiating an object and then running some of the methods that library object has. So you learn all the methods that the library has, and now you're fully enabled to do stuff with what somebody else has written instead of you. So it's really helpful. You can leverage that. Mostly I start with examples and then sort of tinker around from there. There's no reason why you have to try and build something completely carte blanche. So looking through the examples can usually be enough to get you excited about what to make happen next. Fun side note, the servos do run on pulse width modulation, and so they just need to have it specifically timed. So that's what the library does. It lets you run them with pulse width modulation and control these. So what is the next thing for you to do? What's going on next? You just want to output something. So for this last week, we input something, and this week we're going to output something. And so this is going to be another set. I've already built some of them for you in Tinkercad with a bunch of examples for you to go and take a look at so that you can build exactly those. You can download the code. Since I've got Tinkercad open somewhere in one of these browser tabs. No, not that one. And one of these. Here's Tinkercad. We can come back into here. We've got some of these that are already loaded up. And so like a servo is, I think, that example that we were just looking at. Here's a motor and a driver. So one of the things we saw was the flyback diode and a motor. You can totally play around with these sorts of things, and you'll be looking at examples. I'm going to try and constrain the examples that I give to stuff that I know that you have. But in here, if I start the simulation, this is able to adjust what's going on here. And if you look, this is just running on pin 12. And if we go look at our code, it's saying set pin 12 to high and set pin 12 to low and wait 1 second. This is the circuit that it would take to just run this like blink. So it's just blinking the motor off and on. It would be a very bad use for a motor. Like, I don't know where you'd want to have an intermittent fan or some strange motor like this, but it doesn't take a lot to get it up and running. You can totally just get going that way. And then the examples that I gave out last week were block code, but you can totally open it as blocks and text if you wanted to get to how this code works in the Arduino side and just sort of look at it from how you'd loaded it in an Arduino IDE, or you can directly download it and it will download it as Arduino code that will then open directly in Arduino. And it's trying to do that here. So this downloaded and it will open it right into Arduino, just that downloaded program. So there's lots of fun to be had by playing around with outputs. And then once you're feeling confident with these, you can go back to Instructables and start playing what's the driving force, right? You can head through and take a look at how did they make all that happen. If you just hop back over to Instructables Arduino, which let's do this. I'll head back over to the slides. So that's the end of the slides. I want to make sure that oh boy, I got lost in my tabs. One moment. It happens to everybody. let's see, none of these. So we'll close all those. I don't need them. And maybe this one. Yeah. Here's instructables circuits. So you can play around in here. And I think that was the one that I wanted and I just closed. Outputs. This. So the last bit is to output something. So that's your goal for the week, is to try and output something. And that brings us to the show and tell, which is exciting. There's lots of fun things to show and tell. And one of them that I can show and tell first is I've been actively trying to build the Wacom tablet. I still don't know how to say the name. The stand. I'm trying to build the stand. And so that, we made some progress. Here are videos of it going through the process of building. Full screened onto the wrong screen, of course. But there is those images built into a video. So this is it going through, the Gerber is actively going through the process of cutting this out. And so this is in the space downstairs right now. It physically exists. You can go look at it. It is not completely and totally bulletproof at the current moment. So like, you could probably sit on it if you want, but I wouldn't like wander it around in too many weird ways. But this is up and running. So I went through and did this over the course, and that's the same exact video, but this is the process of just getting it through. And then once you have all those things, you have to take it apart. And so get it off. JR popped in at the last minute, but then all of these, I'm able to just run through. And after a little bit of sanding, just to make sure that the edges were smooth, it popped right together. It took some testing, some extra work to make sure that it all worked well. But this is what I've been up to for the past little while, the past couple of days, just to try and make a thing that definitely can be made here. We're going to head into our CNC work a little bit later on. And so hopefully you could take on something like this if you feel like doing it. Now, it was something that I 3D designed. So it came from the start of my brain and then Fusion 360. And then from Fusion 360 all the way into this design space. I used a whole stack of different softwares. There's lots of things that get integrated to make this work, but the payoff is really, really cool. It's one of those things that's definitely a lot to learn, but once you're in and doing it, it's a very exciting thing to have up and running. That's a good question. How long did it take to cut? It took overall, I was here for like 3.5 hours. However, not all of that was cutting. Like the first little bit in the first video, this is the first video, at the very beginning, I don't know if I even recorded it on these. Yeah, you can see up here, this top bit, there were those 4 blank spots. Those were test cuts that I did to see that my fit was just right. Because right now the whole piece is holding itself together without any glue or fasteners. So like I wanted to get the size just right on the pieces. And so I spent a couple of hours or an hour and a half probably dialing that in. And then I had to redo all of my sizes and shapes, which because I did it the right way inside of Fusion 360, it was a couple of clicks of the buttons. So it wasn't like it was a ton of extra work to make that rearranged. But this process is definitely how you go through about taking one sheet of Baltic birch plywood and turning it into a nice big piece of furniture. So it should, tomorrow is another February break day. So fingers crossed, I'll be done and the Wacom tablet will have a new home tomorrow. But that's the game plan. So that's what I've been up to. Let's see. Oh, it looks like we just lost James, which is a bummer. I should have done show and tell last. All right. He might come back. We'll see. But with that, I'm gonna stop sharing my screen. And I want to hear from you all, what you've been up to, how you're doing. If you've done anything fun in the last little bit, any makery things that you've been up to. And we can start with Alina, your camera's on. Do you want to go first?
Sure. I have been catching up on class recordings and looking at slides and stuff. So I haven't done any of the input projects from last week, but I've been kind of going back in time, and so I've been knitting a little bit more. Got back into the wood shop yesterday and went to the women in woodworking lathe workshop, so that was fun. But I don't have anything finished to show yet, so just kind of getting back into the swing of things this week.
Well, yeah, and getting back into the swing is totally part of the game. I'm very excited to see what you make on the lathe. You did a great job with those trays. I want to see what happens.
Thanks. I'm very excited. I have like shopping tabs open all the time of like interesting wood now. So
that's good.
Wallet can survive.
Yeah. There's also some local suppliers. So if you're, depends on what you're thinking, but if you want to buy like a big board that you can turn into something smaller, it can be a good way to go.
Definitely. I've got that link that Arvia shared a long time ago from that guy on Facebook. So
yeah.
Definitely.
Yep. Cool. All right. We've got Norman Arvia around. Arvia, looks like you just turned on your camera. Do you want to go? What have you been up to?
I don't have much to share. I'm right now I'm in North Carolina with my mom, visiting my family. So that's been nice. I actually brought with me here, also going back in time, what's it called? Stuff to make prints out of that you carve into. What's it called again?
Oh, the like block print things, the linoleum.
Yes, yep. I have a few pieces of linoleum here. And I keep saying I'm going to carve into it. So that's my plan while I'm here. And my mom is definitely like a maker, does all the things. So she's sitting next to me. That's why I looked over at her. She's putting floors down in the house. So I might help her with some of that this week if she wants to finish it. So.
You heard it, Mom. She said it out loud.
Yeah, I heard her. Oh yeah. I need to catch up on last week's class. So
yeah, cool. And then when it's a good one to do, it's fun to do remotely. You can play around in Tinkercad, and then if you're, if we connect when you're back, it's easy to sort of rush through inputs and outputs together. If we have to make it all happen in one sitting, we can pull that off too.
Cool. Sounds good.
Cool. Awesome. Have fun in the Carolinas.
Yes, it's warm here, so it's nice.
Oh, that sounds so nice.
Yeah.
Yeah, it's very cold here.
Yeah.
All right. Norm, how about you? What are you up to?
Yeah, like everybody else, I spent time looking at your seminar materials and going back at the original Arduino Upshield notes about the the programming and whatnot. So I was slugging through that stuff, and I've got in the background a notion of doing storage modules that I've mentioned before. So I've been, just doing various boring things that don't bear explanation really. Cutting wood to size I think I might need, running a couple 3D prints to see if they might be useful for ornamentation. So, did some things, but didn't result in anything interesting to say.
That's all right. Sometimes you just have weeks that are all about the nuts and bolts of like moving a project forward, and it's not, there's no like big fancy picture at the end, but it's still good work. So it sounds like you had one of those weeks.
I will say my daughter says that she was the 11th person to enter Australia after they opened the borders. She was, going with her boyfriend to visit his family. He's been away for 2 years. And they knew that the border was supposed to open, which means that the kind of embargo and visas went away and you could enter normally. But that wasn't true when they got on the plane in LA. But it became true. They knew they believed it would in midair. And so she was number 10 off the plane and through immigration.
Wow, that's bonkers. And very congratulations to her and to them. That sounds lovely. To go be in another part of the world.
And it's warm.
And it's warm. Yep. Yeah. I think it, it's starting to happen. I just heard that Leor is headed out on vacation, and so hopefully nothing breaks. Like I think people are starting to make the travel happen again. I'm cautiously optimistically going to go get my passport tomorrow. It expired in the middle of the pandemic, and I didn't think but now it's time to get it re-upped again with hopes of maybe a normal future. That sounds lovely. All right.
Apparently you have a year to use your expired passport. That's what the TSA agent told me. But don't take that for they told me that when we were here. They're like, no, if it expires, you have a year to get it. And I was like,
yeah, actually, I spent part of today trying to get my global entry thing updated, and it doesn't expire for a year. But being kind of nerdy, I did it as soon as you could, which is a year before expiration. And they told me, well, we don't know who you are. We've got no record of your email. Be aware that there are long delays before we can ever, deal with your complaints. So I've got a global entry card that works and will work for a year. But I'm very glad that I started a year ahead of time to do the renewal.
Yeah.
Just so glad you said that, because I forgot about mine. I get to check mine.
Yeah. This is what it's like at the close, hopefully, fingers crossed, towards the end-ish of a pandemic. Everybody remembers how to travel again. All right, Elisa is in the room, and so we want to make sure that she gets to show and tell. Well, but that's all right. But you can chat about what you've been up to.
So, I mean, whatever it is you saw before, it's all still just in progress. But so I made a visit to the hardware store and came back with all manner of sandpaper. So I'm just trying to sand the cutting board. Once it went through the Shapoko, all the different areas are somewhat, the transitions are a little bit sort of stepped down and irregular, and some things are a little rougher. So I'm just trying to get in there and not do damage while I try to make it smooth. So I'm here tonight to sand so I don't have to make the mess at home. And I'm still working on, connecting that jewelry you see me working on. I made some jump rings, I guess yesterday. I'm having a hard time finding brass wire. It's got to be thinner than an 1/8 inch diameter and about 36 inches long. And what you do is you bend it kind of this shape, and you put it in a vise and you turn it, and you hold your silver wire, you pinch it in there, and then you start turning it, and it makes a coil. Then you cut a slit on the end of the wire, and you take your jeweler saw and you start sawing. And as you saw only one edge of it, not both, you end up with rings. So I have one. So I mean, I didn't, but I'd like to make other diameters. So I don't know where to find this kind of brass rods that are that thin. I used to be able to, but now when you call a place, these places are called shaped wire, these companies, and they don't want to deal with you, because you're not a company. So, but anyway, so I made the jump rings, and it's on the home stretch. So that's pretty much it. Also, I'm gearing up for hopefully on Thursday, cutting on the laser cutter, that woodcut, 2-blocked woodcut thing.
Oh, exciting.
So
Art, print.
yeah, yeah. So if you're around on Thursday, good. Yeah. We'll be here. So that's pretty much it. Yeah.
Right. Yeah. That's the process for making rings. I think I've made sort of funky rings when I've needed to out of wire, but it makes sense to do sort of that winding process.
But you're always going to need something to shove the coil in that where you can start sawing.
Yeah, that makes sense. Huh. Yeah, that's a cool process. I wonder if artists and craftsmen across the street might have some of those things.
None of them did. I guess I could call and ask.
Yeah.
If you go on the website of Lowe's, they have it, but then when you show up at Lowe's, they tell you. But nobody can find it.
Yeah, yeah, the like metals in Lowe's are pretty hard to find. So bummer. Yeah. All right.
With Home Depot, you can order it at Home Depot and they'll find it on the shelf and put it in a waiting place for you. They'll email you when they've found it and it's out. I don't know if Lowe's does that.
Well, that's what I was trying to tell those guys, who were helping me, but
The,
never.
the other is you can go, I should share my screen again because I'm gonna let me share my screen real fast. And is to go to this is the most expensive possible way to get it. You can go to McMastercar and then order from them. And so you can get any size brass rod that you want. And so, I mean, you can get from them ultra machinable hex bars, brass rods and discs. There's lots of different ways that you can get it depending on what you want your diameter and your thickness to be.
So it's not that expensive, 3 feet, it's only $369, that's what I expected.
Yeah, cool. Then you're going to have the shipping costs, which is going to be, so I would say buy a lot if you want to cut down on the shipping costs. I used to live there in Strongsville, Ohio, which is like 10 minutes from where I used to live. You could go pick it up. You could pick it up, but it is not going to be available here for walk in and pick up. Yep. You can totally get it there when you're there, or just have them ship it to your sister. The shipping will be much cheaper. So any of those are totally reasonable options. If you ever want to buy some weird thing, McMastercar is absolutely the place to go look for it. You'll pay more, but they will have it for sure. So yeah. Awesome. It sounds like we've been doing lots of cool things. This week is outputs. Next week, I do want to draw a little attention to. Next week is going to be composite materials. And it's really cool. It's definitely one that takes a bit of time to do. So I think we're going to need to have our talk about it session. And then maybe on like Thursday night or that Sunday, we'll do the actual like compositing together. Because it's sort of a weird, messy process. Like once you start the epoxy, there is nothing else that matters in life until that epoxy is set. It's a weird scenario. So we're gonna go through all of that, and we'll have the normal class on Monday, and then probably on Thursday and on Sunday, just so that if you can't make one, you can come to the other. If you want to do both, you could. We'll try and make composite bowls or composite plates in it, or if you have something else that you want to wrap in a composite, we can totally do that as well. So if you have cool ideas, we've got some materials. Basically, we're just going to take fabric, smear in epoxy, and then enclose it in a vacuum sealed bag. And so that way we'll get sort of a compression epoxy composite, and it's pound for pound stronger than steel, which is pretty crazy. So that's the magic of composites. It's why airplanes are built out of them. And we'll figure out how to do that next week, which is lots of fun. And sort of Arduino can be hard work sometimes. This is the payoff for the hard work. So that's the plan. I'll come out with more details for that, but it should be pretty standard times at like 5:30 is when I'll start, but maybe we don't start the composites at that time on Thursday, start a little later, 6:30 or 7 something. And then Sunday we'll do more in the afternoon, maybe around 3. But those are totally just loose times. I'll put out messages into Slack, and if you have strong opinions about what time, I'll ask what time works best for people, and we'll figure out something for Thursday and Sunday then. So that's the plan. Outputs this week, and then composites next week, everybody. So have a great night, and we'll see you soon. See you, everybody. Bye.